Good evening and welcome to the third week of the 2023 Science for Alaska Lecture Series. Tonight, UAF Research Assistant Professor Doğacan Su Öztürk will present Satellites to Cell Phones, New Ways of Understanding the Aurora. If this is your first time with us, we're glad to have you here. And if you've been with us the last couple of weeks and in past years, we're happy to have you back. I'm Rod Boyce from the Geophysical Institute's Public Information Office. For those of you who can't see us tonight, or see me tonight, well, us, I guess, as part of the UAF Department of Equity and Compliance recommendations, I wanted to provide a brief physical description of myself. So I kind of thought I might do like 6'2", tan, muscular, 30, something like that. But no, I'm close to retirement age, wearing blue jeans, glasses, and I'm wearing my Geophysical Institute hoodie. It's dark, and down the left arm it says Geophysical Institute. And no, I don't have the full head of hair. So, all right. So, before we go much further, we want to acknowledge the Alaska Native Nations upon whose ancestral lands we're located tonight and where our campuses reside. In Fairbanks, our triathletic campus is located on the ancestral lands of the Dene people of the Lower Tanana River. We're happy to be able to be back in person and to host many viewers from all over, well, lots of places, and hello, online audience. Okay. The lecture series is in its 31st year, and we'll be providing a science talk every Tuesday through March 7th. The lecture series this year is sponsored by the Geophysical Institute, the Triple Horn family, the Alaska Established Program to Stimulate Competitive Research, you may know that as EPSCoR, Vicki and Vicki Weinstein, and Life Water Engineering Company. So a big thank you to all of our sponsors, and these events can't really happen without our sponsors. Just a couple of quick announcements tonight, and they're the same ones I read to the audience each week, so maybe at some point some of you could read them back to me if you've been here long enough. If you have a cell phone, now's a good time to silence it. That way you won't disturb your neighbor or the presenter tonight. The lecture is being recorded. The video will be available for viewing online at the GI's website and YouTube channel shortly. Restrooms located outside the auditorium to the right, and I know around the hallway here there's a few a few steps away. There's an emergency exit out the back of the room, and regular exits are to the left and right at the top of the stairs. You were given a piece of paper that has a survey on how you heard about the lectures that we would love for you to fill out, and that can help us on what we do in coming years. On the opposite side of those surveys, you will find a spot to write questions you may have for our guest tonight. In addition, there's a QR code you can scan to view the live captions on any device with internet access, such as your smartphone. The formal lecture will last about 45 minutes, and there will be time for some questions afterward. You can raise your hand to ask questions verbally, and either myself or my colleague Ray over here in the corner, she and I will bring a microphone to you, or we'd be happy to read your question for you. And if we don't have time to get to all of the questions, you can leave it when you leave tonight, and we'll get an answer for you. So, with that said, I would like to introduce Dr. Denise Thorson to welcome tonight's speaker.
Thank you, and welcome everybody to Scheibel Auditorium. It is my great pleasure to introduce to you Dr. Doğacan Öztürk. I have this thing I'm supposed to read, which tells us all about her life, starting from when she was an infant. No, I won't go that far back. Doha comes from Istanbul, Turkey. She obtained a bachelor's degree in aeronautical engineering at the Istanbul Technical University in 2012. She received a PhD in space physics and a conjugate PhD in scientific computing, and a certificate degree of diversity, equity, and inclusion leadership from the University of Michigan in 2018. Her PhD focused on understanding solar wind dynamic pressure control of the coupled magnetosphere, ionosphere, thermosphere systems using magnetohydrodynamic modeling. I managed to spell it all out. Upon graduation, Doa joined the NASA's Jet Propulsion Lab as a postdoctoral scholar in ionospheric atmospheric remote sensing group. There she developed a high-latitude input for mesoscale electrodynamic framework, a code library that enables incorporating measurements of electric fields as boundary conditions in the general circulation model. In 2020, she joined the Geophysical Institute, and we're lucky to have her, and has been working as a research assistant professor since 2021. Öztürk's research interests are magnetosphere, ionosphere, thermosphere coupling, interhemispheric asymmetry, mesoscale variability of the near-Earth environment, application of machine learning to heliophysics data, citizen science, and education. She's a Fulbright scholar, and she was awarded the Martin Luther King Spirit Award given to students who exemplify leadership and vision of Dr. King through their commitment to social justice, diversity and inclusion, and Dr. Tae-Soon Lee Award for her academic achievements during her time at the University of Michigan. So again, I'd like us all to welcome Dr. Öztürk, and I think you'll have a very enjoyable talk this evening. So welcome.
Thank you, everyone. Thank you, everyone, for coming in person and for everybody who is online. Again, for those who can't see me, as part of the UAF Department of Equity Compliance Recommendations, I will provide a brief description of myself. I'm short, I have short curly brown hair, I wear glasses and a black suit. So I was told that you might be interested a little bit more about where I am from and how my journey unraveled. So I was born on Earth. Here you can see, in particularly, I was born in the Asian part of Istanbul, Turkey, in this particular hospital that no longer exists. But for my bachelor's, I went to the Istanbul Technical University, which was on the European side. So every day I commuted between continents. And it is some fun fact that I have about myself. During my bachelor's degree, I earned an Erasmus scholarship and studied at the Netherlands Technical University of Delft and aerospace engineering there. And in 2013, I made my way across the pond, as you say it, and arrived at Michigan Ann Arbor to study in the Department of Climate and Space Science and Engineering. After receiving my PhD, I went to the sunny California, really liked it there, and went to work at the NASA Jet Propulsion Laboratory around 2 years. And in the height of the COVID-19 pandemic in September 2020, I made my way into the north to Geophysical Institute. So you might have heard about Turkey a lot in the last few weeks because of the two big earthquakes that happened. And the epicenter happens to be my mom's hometown of Kahramanmaraş. So the last few weeks have been really tragic for everyone who is from Turkey. And what makes it really difficult is that scientists have been predicting a big earthquake at this region for a long time, even though the fault line that produced this earthquake was silent for about 500 years. And the people who lived in this region also knew about the dangers of the earthquake, but somewhere along the line between scientists and the people who are living there, something got lost, and it has something to do with policies, which brings me to the ProSwift Act. This act became public law in October 2020. The ProSwift stands for Promoting Research and Observations of Space Weather to Improve the Forecasting of Tomorrow Act. This basically tells us any phenomena related to space weather which can threaten the United States infrastructure is something that we should study and be prepared for. So how does it relate to Aurora, or QGIAT in Inupiaq? So Aurora, as we know, is a natural electrical phenomenon. It's basically an electrical current system in the upper atmosphere. We see it as basically light displays that are generally greenish with some purple and reddish hues, but this is a space weather phenomena that is directly related to how geomagnetic system couples. So we said that these auroras are electrical current systems that close through our upper atmosphere. What this means is that these current systems are strongly associated with electric fields and magnetic fields. at certain times they can be so strong that they can induce magnetic, they can change the Earth's own geomagnetic field and induce current systems in the ground. So any of you who are familiar with electrical circuitry probably knows what this symbol means. This means grounding, right? So if we have an electrical system and if by any chance we have a switch going wrong or any excess current in the system, through grounding, we get rid of this excess current system. So this is our backup plan. If something goes wrong, we ground these electrical systems and we get rid of this extra current that is loaded on our systems. When we have very strong currents in our upper atmosphere that can induce currents on the ground, it means that we no longer can rely on any circuitry that depends on grounding, right? So this is when ground starts feeding currents back to your electrical systems. So this affects our transmission lines, this affects our pipelines, affects our phone lines, railroads, you name it. So this is why it could have very drastic effects on our infrastructure. So especially associated with aurora, these geomagnetically induced currents at extreme times can go affect all the way to basically North Florida in this case. So this is a very extreme event that happened on March 13, 1989. And during this geomagnetic storm, we can see that the auroral oval, or typically where you see aurora, extended way south. You can see most of the southern states have been under the auroral oval. So what this could do to a system is displayed here. This is the New Jersey nuclear plant transformer. It basically melted during this storm event. It causes especially damages around $10 million, but again, there is also a threat to the human life and the operations that we have in these instances. So that is why we want to be able to better understand what leads to an aurora and be able to predict them. So we know that these geomagnetic storms have something to do with the sun, mainly the solar activity. So here what we see is coronal mass ejections, and you probably have heard about them. Coronal mass ejection is hot tenuous plasma that is emitted from the sun surface. So you can see this as basically like a flamethrower, and these coronal mass ejections can propagate in the interstellar medium and affect each planet along its way. So where CMEs originate, these coronal mass ejections are called sunspots. These are basically points at the sun's photosphere, the part where it is producing light, and they appear as very dark points. That's why we are able to see them through our telescopes that observe the sun. So these are regions where we have very strong magnetic fields, so it starts lifting up plasma from the sun's surface to a certain height, and here produce solar activity. Some of these sunspots are as big as Earth or even bigger. So that is why we have a good track record of this number of these sunspots, which is a good indicator of solar magnetic activity. So here you can see that if we line up the number of sunspots from a certain time, we can see a cyclic behavior. Here, this plot particularly stands from 1996 year, and you can see the northern and southern hemispheres. And here we have the sunspot numbers for both north and south hemispheres. So you can see there's 10 to 11 year. It's not very strict, but there is a cyclic dependence of solar cycles. So you can see, for example, the sunspot number was very low in 1996. Similarly, between 2007, 8, and 9, and around again 2018. We call these intervals solar minimum. Where sunspot number is lower, we expect less intense events like coronal mass ejections. So this is one way of predicting how likely we are to have some significant events that could create geomagnetically induced currents or strong aurora. And there are the intervals where you can see sunspot numbers increase significantly. These are the intervals where we have strong solar activity, which means that coronal mass ejections are emitted more to the interstellar space, and then approaching Earth and interacting with Earth's environment is more likely at these intervals. So you can see previously it was around 2013 to 2012, and we are expecting the next solar maximum to be around 2024 to 2025. So this is one way we can start predicting what is going to happen with the aurora. Next thing we have to look at is the interaction of these coronal mass ejections or other phenomena that is emitted from the sun with the near-Earth environment. So this ejecta is basically supersonic, so it forms a shock. That is the one way that we can slow down the material that's coming from the sun. That's one way that the material gets shocked and slows down, so that's the first line of defense. The second one is Earth's magnetic shield. So as we know, Earth is like a compass. It has a dipole-like magnetic field line configuration. So the one particular thing about Earth's magnetic field line is it is south to north oriented. So this means that our magnetic field lines extend outward from south and they go inwards at the northern pole. Of course, this is not very idealized shape. Normal surveys of geomagnetic fields shows us a way more complicated picture, but overall we have the polarity established. So what happens is Earth and the interaction with this interplanetary magnetic field creates an interaction that leads to all these phenomena that we see. But these coronal mass ejections have a way of weakening our magnetospheric shield, which is called magnetic reconnection. If two magnetic field lines are forced, if they have opposite directions and forced to get closer to each other, the particles that are attached basically can jump ship. So this creates a new configuration of magnetic field lines. So you would see that this is the same phenomenon that basically ignites coronal mass ejections out of sun's surface, where we have seen the sunspots. This is also a phenomenon that we see a lot across the universe. So here is a brief animation that shows how this interaction unravels. So here at Earth, this is the day side, basically the side that looks at the sun, and this is the night side. And since the Earth's magnetic field sits in the buffeting solar wind, it is compressed on the day side and elongated on the night side. So you can see how magnetic reconnection takes place, especially when the interplanetary magnetic field is opposite to the Earth's own south to north dipole. These open magnetic field lines also propagate with the solar wind to the tail and form a new reconnection line, because now in an opposite direction, because they are again forced together because of the added magnetic flux. So magnetic field lines really like to not be stretched too much. They want to have a dipole configuration if they can. So when they are broken and reconnecting, the particles they have also get energized like a slingshot. So you can see these two regions, the day-side magnetic reconnection region, where we had the first interaction, where you see the yellow lines here. When they are pointing southward, they interact with the Earth's magnetic field line in a manner that will break it on the day side. And on the night side, where we have all the magnetic flux being accumulated in the tail, what we call the magnetic tail, and they are forced to stay together. So here you can see the arrows in the green lines pointing sunward, and here it is pointing tailward. So when these field lines again are forced in a close vicinity, they form night-side magnetic reconnection region and again energizes particles along the magnetic field line. So this is how basically the aurora particles which create the aurora in the upper atmosphere occur and get energized. And we know, based on their energy level, they interact with different layers of the upper atmosphere. If they have low energy, they deposit their energies with the oxygen atoms at around 200 to 250 kilometers. If they're a little bit more energetic, they can propagate further into the upper atmosphere, which is around 120 to 80 kilometers, where they interact with oxygen to create green light this time. And if they are very energetic, we would see them go all the way to 80 to 100 kilometers and interact with the heavier molecules, like the nitrogen molecule. So this process happens to repeat itself very often. Every time we have a magnetic field line, we don't always have to have coronal mass ejections. Whenever we have a magnetic field line that is pointing in the southward direction, opposite to Earth's own magnetic dipole, we start to open the day-side flux and starting to accumulate it on the night side. And the Geophysical Institute's own Suyun-İç Akasofu was the first one to see that there was a repeated behavior again with these auroral patterns. So looking at the films that are developed from certain regions of aurora, he was able to coin this term auroral substorm. So this is not as huge as a geomagnetic storm, but it's a more repeated process called a substorm. What happens during this process is we have an auroral oval forming because there's increased magnetic flux on the night side. The day side field lines open, they accumulate on the tail region, and they start to brighten up the night sky. When magnetotail becomes stable, which is the part where we had that reconnection occurring, we see more dynamic features. Aurora becomes brighter, it starts to form more spirals and different figures, and there is the last portion of this auroral substorm where the flows and electrojet subsides, so we see the aurora becoming dimmer. All of these processes map to the magnetic tail and Earth's magnetotail and the processes there. So here you can see when the day side flux opens, this is called the growth phase. It starts to accumulate on the night side and starts to brighten up the auroral oval. When we have the reconnection happening in the near Earth region, we started to see all these features because all the plasma in the magnetotail, millions of kilometers away, starts to move, and we see their foot points basically on the upper ionosphere. And after this plasmoid forms and is released, the flows and electrojets starts to subside. So bringing this all together and about how we are going to be predicting auroral activity and mitigate its effects, here now we are equipped with 4 different things. So based on this, we can tell when the conditions are going to be right for aurora. The first one is looking at the sunspot numbers. As we have seen, there is an 11-year cyclic variation in the sunspots. When we are in a solar maximum, we expect more activity. For example, in 2024 and 2025, we are going to likely see more aurora happening. The second way of seeing these is looking at the occurrences of coronal mass ejections and flares. So here you can see a coronagraph image captured by NASA, SOHO spacecraft, and you can see this coronal mass ejection. These are generally a few hundred to 1,000 kilometers per second ejectas, so we can estimate a few days ahead if a coronal mass ejection is going to arrive at Earth, so it gives us maybe 2 to 3 days leeway into predicting what can happen. Next, what we can do is, as we have discussed, when the interplanetary magnetic field or the magnetic fields coming from the sun and the plasma coming from the sun has certain conditions, we are more likely to see aurora because of this magnetic reconnection phenomena. So here we have 3 solar wind monitors, Discover, ACE, and Wind. And what they do is they measure the plasma density, velocity, temperature, as well as magnetic field vector. So when we look at these data, these sit between the sun and Earth at a stable orbit. So it gives us, again, a few hour head start when if they are observing really fast solar wind, really hot plasma coming, or very prolonged periods of negative IMFBZ, negative as in southward configuration. So then we can expect to see aurora. Based on these properties, NOAA and NASA provide regular forecasts of space weather. But again, it could be still very unpredictable, because if you look at the aurora forecast, the state of art we have is an auroral oval, which gives us a probability of aurora. It doesn't tell us the type, location, or time of aurora. So here are the all-sky cameras that we have. This all-sky imagers, basically a bubblehead type of configuration over cameras, and they are, we have this chain called TEMIS that is located in the Northern America and Canada here. And when we look at what they are measuring here, you can see all these finger-like structures, something coiled, something unraveling again. So at certain instances, some field of view of these cameras look very stable, very quiet. Sometimes they get really dynamic. So predicting this, what type of aurora we will see, where we are going to see it, and where the location, when we are going to see it, are really still difficult to predict. So we can look at aurora in a few different ways to understand which phenomena they are associated with in the magnetotail, which can help us understand what's the generation mechanism. The first one we have is the classic arc aurora. It's very bright. You can see the edges very clearly. The boundaries are really clear. We have the corona spiral or substorm. It has both 3 names. These structures, they are basically when we call our friends and say like, oh, you should go out, you should look at the aurora, it's really pretty. This is very short-lived, again. We have the bead aurora, which is also known as a string of pearl configuration. This again maps to a different process in the magnetosphere. And we have all different sorts of aurora, like the omega aurora, which are like U-shaped auroras that we see. We have pulsating aurora, almost standing still type of aurora. The torch aurora, which extends from this omega aurora, and the black aurora, where the emission significantly drops. So all of these aurora types exist within that oval prediction that we provide. So we don't have the capability yet to say, okay, we're going to see this particular type of aurora at this time and location, because we do not have the capability to survey all the magnetotail at the moment. It's a really huge amount of area. So we can't really pinpoint where that reconnection is happening, what the particle energies are like at every point to be able to give an accurate prediction. But one thing we can do is we can look at the three distinct energy levels of these incoming particles and go from there to see how these phenomena that we know how it's more or less generated could be predicted. So one of this type is the diffuse aurora. This is when the particles we have are scattered into the loss cone, which means that they are normal loss mechanism of an aurora. We don't see an acceleration mechanism. This is when you look at the sky and you see a dim greenish hue. Next, we have the discrete aurora, like the ones that we have seen, the spiral aurora. This is very dynamic. We see all sorts of light and we can see different colors occurring at this time. And lastly, we have the arc aurora. This is again not as dynamic as the discrete aurora, and it's not as long-lived as diffuse aurora. So this is again very easy to predict. We can see the boundaries very brightly. So what we can do now is to use image processing and machine learning to classify images and see if we can pull out information about these three different types of aurora. So again, using the THEMIS all-sky imager and camera chain, what Klausen and Nikesh did at the University of Oslo is coming up with a labeled data set where other machine learning models could be generated from. So looking at the images from all-sky imagers, they identified 6 cases where there is the cloudy, or it could be cameras are covered with snow. A second case where there is moon or a really strong light obstruction. A third case where we don't have any aurora or we are able to see the stars. Fourth case is the arc aurora that we mentioned. The fifth case is the discrete aurora. It's the bright, very dynamic aurora. And the diffuse aurora, where we are seeing regular particle shower. There's the 3 different classes where multiple classes exist. Here, for example, we see some arc and some diffuse combined. Here, again, we see something similar, arc and diffuse combined. And here we have some cloudy or moon conditions together. So what this database enabled us is we can start training supervised machine learning algorithms based on that. Previously, all aurora studies are more or less done with one person, a scientist, sitting in front of a computer, looking at all these images and trying to classify them. And we have more than 1 billion of these images. So doing it with human labor is really counterproductive. So what me and my colleagues, led by Jeremiah Johnson, did is we took all these images and trained a new model of machine learning algorithm. This is a similarity search algorithm, and with this, we are able to input any days, any configuration of all-sky imagers, and we are able to predict for each all-sky imager what the probability, highest probability for that image is. So you can see we have a case where there's diffuse aurora, which is correctly labeled. We have very discrete aurora. Here you can see it's correctly labeled. And there are some arcs that are also coded by the model. So this really enables us to process really large databases and obtain a better understanding of how these different types of aurora are generated. And also related with some of the solar wind monitors that we talked about. So this preliminary research results show us that for arc, diffuse, and discrete aurora, we can go back and look at the solar wind monitors and look at what's the velocity of the incoming particles are. Similarly, we can look at different magnetic field configurations from the solar wind monitors and say what would be the distribution or what would be the likelihood of seeing one type over the other. It will also help us generate theories to explain how likely that we are to see a certain type of aurora. We can also look at these distributions at different magnetic local times and see how well we reproduce some of the known phenomena in the literature. So with this method, we are able to almost look at 10,000 or more than 10,000 images. Previously, our capabilities were restricted with only hundreds of images because, again, it was a manual effort. So, of course, these methods or machine learning has issues with itself. We don't always can rely on what the machine is telling us. So that's why we have also launched a citizen science effort called Aurora Click. So this is hosted on Zooniverse, so all of you can go to the Zooniverse and now participate in this project. You have to complete a little tutorial about what the discrete aurora, diffuse aurora, arc aurora looks like, how is the cloudy conditions look like, what the clear sky looks like you see here. And then with your answers, we are able to fine-tune our machine learning models as well. So what will this help us do in terms of understanding aurora and the geomagnetically induced currents? Here you can see that how improved characterization could lead to improved studies of the impact. Here what we have is the probabilities of aurora plotted at the different temporal scales. And you can see that we have basically different probabilities like the arc, clear, cloudy, diffuse, discrete, and moon. And here we are able to look at the kilogram, which is obtained from the all-sky images, and predict what type of aurora we will be seeing during these conditions. So at the end of this interval, after 450, we have this 10-minute interval where we see significant discrete aurora. So you can see the brightness here starts really high up and goes all the way down. So with this kind of aurora, what we can see in the magnetic field measurements that are from a magnetometer at that location are significant horizontal component decrements. So this is around 20 nanotesla decrease over the 10-minute period. And what it tells us is that how effective certain auroral types could be in understanding geomagnetically induced currents. So we can further extend the study of ground magnetometers and geomagnetic field measurements to understand how it relates to aurora and the ground-induced currents. But as you can see from this image, we have a bit of a coverage problem. So here, what you see with the red, the pink crosses and the green crosses are all the magnetometers we have, and green indicates the operational magnetometers we have currently. So here, especially in the west portion of the Alaska, we really have a coverage issue to understand how different aurora types could lead to different geomagnetic field signatures. But here you can see all the high schools we have across Alaska, and especially in the west of Alaska, we have many high schools which we can collaborate with to understand the ground magnetic field configurations better. So this is why we have found this Space Weather Underground initiative. This is an education and outreach program first initiated at the University of New Hampshire by Charles Smith. And here you can see our logo, which shows our aurora classification efforts and our efforts to understand the ground magnetic field signatures associated with them. So we applied this model specifically at UAF to understand geomagnetically induced current systems because this phenomena threatens the higher latitude regions more. So you can here see our team, our students who work really hard, and Whit Reeve, who is the producer of our magnetometers, and Laurie Schoening, who is our education specialist. So the core of this program is producing simple aurora monitor magnetometers. These have a resolution of 1 to 2 nanotesla per second, which is sufficient enough to see all these structures that we just discussed, which was about 20 nanotesla. It is a microprocessor-controlled magnetometer kit, and it has 3 magnetometer sensor output, hence the name 3. It has an LED screen, as you see, and it comes with a pre-cut enclosure box. So our effort is to equip high school students and all other students that we work with basic STEM skill sets. So here you see one of our stations in our laboratory. It's a soldering station with basic equipments. These magnetometers come with a printed circuit board, which you can then teach students how to solder like resistors, capacitors, batteries, and other pin headers. Once they finish their printed circuit board, they can add elements like a keyboard or LED screen, and then they can add also the three sensor components, and you can see that the three-axis configuration to measure the magnetic field in three orthogonal directions. So we offer this program as a free summer school program for high school students, and also as a paid researchership for our undergraduate students at UAF. The first high school student program we had took place in July 2021, in summer 2021 and 22. Again, because of COVID-19, we had strict restrictions around these times. Student activities included learning how to solder, making these cables, assembling a SAM3 kit, testing of these magnetic field measurements, and also learning about aurora and space weather. Our students also had a chance to showcase their individuality and learn more about space weather. Here you can see the magnetometer designs they have made. You can see Bethany made a glacier and aurora to show what her perception of space weather is, and Savion's kit showed like a satellite. We also offer an educator development program. This took place again in July in 2021 and 22. In July, we only were able to accommodate 5 educators, but in July, we had 10 educators from rural Alaska regions. During this, we offer this educator development program at UAF as a 3-credit course with all the fees waived. We try to cover all the airfare, lodging, travel, and per diem, thanks to a generous support from the Alaska Space Grant Consortium directed by Dennis Torsen. And at the end of the program, we provide the SAM3 kits the teachers assembled and support. We provide them the SAM3 kits and other material that will help them develop curriculums. So here you can see, again, based where the magnetometers are based and where our teachers were based in the 2022 program. So at these regions, we significantly lack having geomagnetic field data. So programs like this are very helpful in increasing our coverage in these areas. So we talked about the enclosures and kits a little bit, but we also had a lot of trouble with finding the right deployment for these magnetometers that we are developing. So a science-grade magnetometer, for example, will require a facility on its own. We have to provide electricity to it, Wi-Fi. It needs to be shielded from the elements, and it has to have certain wildlife protection. So this also proved to be a challenge for our SPARC program. We started with a wood crate design, which we soon figured out was not waterproof and was not thermally insulated. So that's why we moved into an anchor type, where we know that our collaborators in the lower 48 usually employ. This anchor type could be insulated because it's buried in the ground, but then it's not possible to deploy these magnetometers at Muter. So we tried to move on to something a little bit more mobile and a little bit more easier to deploy, which was the Pelican box. So here you can see a Pelican box can host all these instruments, magnetometers, the enclosure itself, and the computer that we put in it. But again, at this point, we started to run a little bit out of money, and they were heavy. So that's why our students, Jonah Barkley-Griggs and Austin Cohen, came up with this design called Pillbox. And I have one here with me too. So imagine going from basically a facility to something small like this. So here you can see the details of the design. This was basically developed after a lot of experiments of proximity, how close the sensors could be next to each other without interfering with the signal that we get. And you can see that each sensor could be individually insulated, and it separates our other electronics like the computer from the sensors in this configuration. It also is wildlife proof because it's impossible to open it once it's sealed, and it is waterproof and very user-friendly. It's basically a plug-and-play design for teachers. So we're very happy with how it came off. And you can see that all these components are basically commercial, off-the-shelf PVC pipes that can go along with any kind of 3D printed enclosure that we are producing. It's this kind of orangish hued part here. So currently, we have about 7 active deployment sites. We also partnered with the Sol.NET library and hoping to partner with more libraries in the future. We have one of our magnetometers sitting on their rooftop. We have 3 schools, Eagle River High School, Hobson Middle School, and New Wayland School that has one of our magnetometers. And we have 3 at the UAF facilities, one over Reichhardt building, one at the HARP site at Gakona, and one in Poker Flat Research Range. Especially at the HARP and Poker Flat Research Range, it's really important to have additional magnetometers because they can really complement the other scientific instruments there. And here is, in this plot, you see basically a comparison at the Poker Flat site between our magnetometer and the science-grade magnetometer, which is much more expensive and requires a facility of its own. The orange line shows the Poker Flat data, and the blue line shows our student-made magnetometer data. And you can see that it is able to trace the trends really well and captures almost all the magnetic field variations. Lastly, I want to talk a little bit about the smartphone applications for studying Aurora. Recently, our smartphones become really, really smart. They have a lot of instruments in them, which we can access through an application called Physics Toolbox Sensor Suite. Produced by Visira Solutions. So this is basically a free application you can download on your phones, and with using the compass, you can find the magnetic north pole, go back to the magnetometer, and hit start, like this plus button to start recording. The resolution here is microtesla, which is 1,000 times lower than a nanotesla. So it's a little bit coarse, but it is a great tool for education. So what we do with smartphones is running campaign events. So we had our first campaign event at the 28-29 October 2022. This is led by, again, Jonna Barkley-Griggs, Austin Smith, and Austin Cohen are also helping with these campaign events. So what we do is we go to Geophysical Institute's Aurora Forecast website, and when we have the right conditions with the oval configuration for high probability, we designate that day to be a good day where we were going to expect activity, and we start recording the signatures of the magnetic field variations. Here you can see in green line measurements taken with an iPhone, and again purple line you see the Poker Flat science-grade magnetometer data. And I want to remind you that the iPhone magnetometers is in microtesla, so it's 1,000 times more coarse than the science-grade magnetometers that we have. And you can see they were separated in space, so we are able to capture a spatial difference between these two data. And we are also able to capture the frequencies after the high frequencies are removed. So again, with smartphones, it's really a very good technique for us to be able to look into these geomagnetic field variations. Lastly, I want to talk a little bit about our collaboration with the UAF Summer Sessions and lifelong learning. So this is a bunch of classes that are offered for different age groups through UAF. And we will be teaching a Northern Lights course. And this course will include hands-on activities for an intuitive understanding of Northern Lights. So here you can see we have some conductive dough to make different layers of the upper atmosphere. There will be electric circuitry design. So using light, electric fields, magnetic fields, we are going to talk about sun, Earth's magnetism, and aurora. And there you can see the marbles, jellos. So it will be hopefully an intuitive way to learn more about aurora. So with that, I want to acknowledge my collaborators who had been working with me on this project. On these projects, and here are the image credits if you didn't catch them. Thank you, and if you're interested, please check out these links.
Thank you, Doa. Great presentation. I always learn something every week here at one of these presentations. Before we do questions, I did want to kind of let everybody know that we've got about 83 people in our online audience tonight on Zoom and in other platforms. And let's see where they're coming from. We have Paula in Kamano Island, Washington, Amanda in Oahu, Hawaii, Patent rosemary in Salt Spring Island, British Columbia. This is just some of them. I'm not going through all 80-something of them, so don't worry. Luann in East Tawas, Michigan. I'm sure I mispronounced that. Sue in Homer, and that's our former public info officer at the GI here. Shayna and Doug in Homer. Betsy in Cripple Creek, not far from here. Eileen in Tacoma. Terry, a former Fairbanks and now in Ashland, Oregon. Courtney in Fairbanks. And Roxy calling in from Fairbanks with her puppies. So there we go. All right. A reminder on questions, raise your hand and we'll bring a microphone to you. My colleague and other microphone fairy, Ray, is somewhere around here. There she is. Or you can write down your question and we'll be happy to read it for you. And Ray will also be reading any questions from our online audience. So, all right. We have any hand? There's a hand up in the back. Ray is going to run up there. All right. Oh, in the front. Okay.
Quick question. So when you're talking about the magnetic field and how when the shock wave from the coronal mass ejection hits it, it splits apart and it creates the energy that does the aurora, what happens, how does it reconnect again on there? Does it need energy to do that, or does it produce energy again when it reconnects?
So the shock forms ahead of the Earth. It basically, let me go back to the animation. That's a very good question, because what happens is it creates a magnetic flux deficiency on the day side. So we can only strip away so many magnetic flux, and what it does is solar wind carries the magnetic field with itself. So once that oppositely aligned magnetic field lines start to break, you can see the green lines are carried towards the night side, right? So it starts accumulating them here. So imagine this like squeezing a toothpaste, basically. So it goes to the front again because there's a depletion now there. So there it forms a flow from the night side to the day side back again to replenish the magnetic flux on the day side.
Okay, we have a question up in the back here.
Thank you. I've read that the magnetic poles may be reversing or in the process of reversing. I'm wondering, first of all, how do we know that? And second of all, if it acts as a shield against solar winds, what happens when, I guess it decreases before it flips? What's the time frame on that if it's happening indeed? And then what happens to our shield in the meantime?
Thank you. That's a very interesting question. So the variation of the magnetic poles takes more than a few thousand years to happen. It happened around 183 times since 183 times as much as we could trace back through the fossils. So what happens is you can see that Earth's magnetic field is not very clear cut, and we have something called asymmetric reconnection. So when you start to flip the Earth's magnetic field line, let's say it is rotating in a circular sense, we can have different configurations. So in these situations, we'll have something called asymmetric reconnection. Here, if we go back to this, schematic, here you can see that if the magnetic field lines were not southward aligned, if they had an angle with each other, there would still be regions where the magnetic field lines are opposite to each other. So we will start seeing that scenario more often. It won't be like a day-side reconnection here between north and south, but it will be 45-degree north to east, for example, interacting with Earth's magnetic field, which is rotating to the south to west. So we will see the shifting of this day-side magnetic reconnection region from the equator and the tail, where it's basically going through the Earth and separating it into half. So we will start seeing the shifting of that plane, but it will still be protecting us.
All right, any other hands up? We see? Yep, okay.
Great presentation. Winter tourism is becoming really, really important in Fairbanks. And the apps that people use for aurora prediction are really good. How does that, where do they get their data from, and how does that relate to some of the data which you're showing from GI? Because I do use the GI website for looking at auroras. How do those all connect together?
Thank you. So yeah, that is also very interesting. So the first thing we look at is the sunspot number. So that's where we can say, okay, 2024, 2025 will be really good for winter tourism in Alaska, Scandinavia, North Canada. So the next thing we do is, again, some of these applications use the coronal mass ejections, and they use a model called Enlil, which is a fitting algorithm. So what it does, it looks consecutively at these images, coronagraphs, and try to estimate between two images and their time steps how much the coronal mass ejection moved. From that, they do divide the Sun-Earth distance into the velocity they found to kind of give an estimate when the coronal mass ejections will be arriving Earth. Other than that, we have these spacecraft, and when these spacecraft started to see the southward interplanetary magnetic field connection, like you see here, that is an indication. So it's not important if we see like a 1 minute flip, but if we see, for example, half an hour constant negative, as we call it, negative Z component of magnetic field recorded ahead of Earth about 1 hour ahead, we know that in the next hour or so, we will be able to see strong aurora. So on top of that, we have models that propagated these coronal mass ejections, like you see here. It is called the Enlil model again. What it does, it tries to simulate the trajectory for this coronal mass ejection. And we will have an estimate of the velocity and temperature. So if it arrives at Earth in a very high density cloud with very high speeds, it will also send you an alert saying that there is a very fast solar wind right now, or there is a negative Z component. A very long answer to your short question is this one. Yeah.
Are they using the same data that you're using, or where are they generating their own data?
It depends on who is giving you the estimate. Yes. So yeah, we generally use all the NASA and European Space Agency spacecrafts to predict these. And their models, which relies on the probability of this auroral level, same as the GI forecasts, rely on mostly these solar wind monitors and the models, statistical models that are developed as a part of it.
I'm told we have an online question.
Yes, we do. A question from William G. on Zoom. What determines the orientation of the sun's particles, and why does it change even during the same night?
So if I'm understanding correctly, it's a question about the incoming solar wind and what creates its magnetic field orientation, right? Okay, so what determines it is how the coronal mass ejection is ejected from the surface of the sun. Again, we have a difference in polarity between if it's emitted from the northern hemisphere of the sun or the southern hemisphere of the sun. And when these coronal mass ejections are expanding, they are covered with twisting magnetic flux ropes. So it's basically like an electric saw. So we can see a northward or southward aligned. It is I wouldn't say pure coincidence, but there are theoretical models trying to simulate those, but it's a basically rotating magnetic field line in the center of a coronal mass ejection. So we will be interacting at the Earth at different portions of that circular magnetic field. So at some point we can see the northern field or southern field because it's a coiled structure.
All right, any other hands up? Oh, I see one there. Ray, you're closer. Microphone fairy will come around.
Line question as I make my way down. Angela on Zoom asks, is there artificial aurora?
Are there artificial aurora? Is that the question? That's an interesting question. One study using the HARP radar that we have at Gakona was to try and create artificial aurora. And this artificial aurora, we cannot really generate enough power to create artificial aurora, but we can trigger certain regions where here, as you can see, these magnetic field lines will map to this interface where it is likely to produce aurora. So from the ground, we can try to heat those regions and send some signals, but yeah, there's not really a common thing.
We're new to Fairbanks, and we've been wondering, like, yes, we have apps and we know what a website is, but is there like social media? Is there like text messages? Like, hey, the aurora's out. Go out and see them right now. Like, how do we know that? Because that's generally what it is. Because sometimes I'm like, I'm not awake at 3 or 4 in the morning. And I wake up the next day, it's like all these wonderful photos.
So again, there are a lot of community groups like on Facebook that tries to look at aurora. The other thing is there's a group called Aurorasaurus, like the dinosaurs. So you can go to Aurorasaurus website, which streams all the Twitter feed where aurora is mentioned and verifies it using citizen science. So if it's an actual aurora spotting, it will be a verified tweet and will have a geolocation tag to it. So that's what you can use. For us, we generally use this all-sky imager located at Poker Flat. So you can see in real time what the aurora is like in the Poker Flat without light contamination. And I would say if you see something like this, let's go back to the arc aurora. So if you are seeing something like this, which would occur something like that in our all-sky camera, it's likely that in the next hour or so you might get a discrete aurora following that.
All right, any other hands up? Oh, I got one here. Okay. There we go.
Last summer, he opened up the HAP station in Gakona to visitors. Will that happen this summer? They opened it for 1 day. And likewise, up at Poker Flats, will they open that up for visitors again this summer?
That I'm not sure if there will be an open house, but there is opportunities for students to have summer schools at HARP Gakona site this year.
Are those facilities related to Northern Lights?
Poker Flat is basically a research range that we do a lot of auroral research. It's primarily a sounding rocket launching range. We launch rockets from there, sounding rockets, into the aurora to understand its electric fields and magnetic fields and energies of the particles better.
What does the HAP do down in the Gakona location? What does that HAP system do down there?
I'm not very familiar with the research that is being done at the HARP site. It is mostly in the very low frequency range where I look at more ultra low frequency ranges. These occurrences are a little bit like the longer periodic behavior. So the type of research that we are doing at the HARP site is more on the expertise of other researchers.
Okay, thank you very much.
Regarding open houses at any of our facilities, you can just stay in touch with our Public Information Office website and we'll give you plenty of information when we have that, all right? Any other questions? Any other hands up?
I'm Pam Miller, and I guess it was last week, did that. I'll just look one more time outside, and there was one of those, I'm just learning the names of the band, and it was incredible. Very cold, a little bit of wind. The next day I read the paper, I happened to read the Washington Post, and they had a picture, this is where my question will come in. They had a picture of a solar tendril that was somehow extraordinary. I didn't bring the article with me. But that night I said, well, last night was good, maybe this night will be good. And what you're calling the one that's just like God coming out of the sky,
Spiral?
Just coming down like this, and all, yeah, like that. I'd never seen it like that before. And do you think that what the Washington Post had said was a remarkable amount of plasma coming out of the sun may have been related?
So, yeah, when we have coronal mass ejections or this ejecta coming from the sun, they are likely to be more vibrant and more dynamic, for sure. What happens is that along these magnetic field lines that we have talked about, it's a mix. We have particles that are coming from Earth's own atmosphere, that are in our own radiation belts, or we can have particles that were in the, like, tied to these open magnetic field lines. So if they are very high energy, which can penetrate lower into the atmosphere and create more purplish hues, they are most likely to be in that high energy band that might be coming from the sun or accelerated through the processes that are associated with its travel.
All right. Oh, there's another question. Ray, where are you? Here comes the microphone fairy.
Thank you for the presentation. I was wondering, going back to your disaster, the northeast area where they melted all the transformers, while that was a very major storm, if I remember right, that was an 8 or a 9 on the scale. What are you seeing potential for more of that or any of that, even at a lower scale, that could actually impact the electrical structures? And I'm looking at it from an emergency management aspect. What kind of disasters can I expect from major oral activity?
That's again, requires a very long answer, I would say. So geomagnetically induced currents are one part of the picture. During these events, I mean, after this strong, it's called like the big Quebec blackout as well, where the Hydro-Quebec power lines were down for more than 8 hours. So like events like these is a wake-up call generally for independent system operators. So there are a lot of policies and regulations with the independent system operators on power lines and transmission lines. It also depends on how they are aligned. For example, in Alaska, we have north to south aligned pipelines and transmission lines. So they are not affected as much from the horizontal component that we talked about from Aurora. But there are, again, regulations in place to accommodate any geomagnetically induced current up to KP of 9 during these type of strong events to accommodate that excess current systems. But we are still trying to find ways, especially, for example, if Alaska were to expand the transmission lines in the east-west direction, that is something that we definitely have to look at. So that orientation would be something that we would expect to affect the geomagnetically induced currents. Another thing is they really affect the GPS and the communication because they heat the upper atmosphere a lot, which lifts up the upper atmosphere. This is where we are trying to reflect our signals from. So if we are moving the goalpost for the signals, which affects all the telecommunication operations as well. So apart from a geomagnetically induced current, I would expect uncertainties in the GPS data and problems with communicating through radio, especially with smaller aircraft in these scenarios. And then lastly, because of the significant ionospheric heating, we have more denser portion of the atmosphere lifting up as well, which is known to cause satellite drag, aerodynamic drag on satellites, which eventually is the same mechanism that led to the 39 Starlink satellites fall, which Paul Bernhardt in the first week was talking a little bit about as well. So those are some other not immediate effects, but something we would expect in an event like this.
All right. Any other hands up? No?
Questions from online still. So Lacey F on Facebook asks, what is the black aurora? I've never heard of that before.
Yeah, black aurora is, unlike the name suggests, it's not a lack of aurora. It is where we have incoming particles that creates the aurora, right? Black aurora is more, could be regarded as anti-aurora, where we have particles that are not associated with downgoing particles, but mostly upgoing particles. And it is a phenomenon that's been studied after more recently, especially I think Don Hampton at UAF has a new grant to study black aurora as well.
And David L on Zoom asks, what was the app that indicated the magnetosphere or magnetic orientation?
The application that I didn't particularly talk about an application, but going through NOAA or NASA space weather website, especially solar wind, looking for the solar wind monitors, searching for NOAA Discover would lead to that solar wind monitors that will indicate these conditions in the near Earth magnetic field.
All right. Any other questions? I'm going to ask one last one here. All right, unless another hand pops up. But of all the different types of aurora you've talked to us about this evening, is there one that's most intriguing for you from a researcher's point of view?
Yes. So we didn't talk about it, but there's an aurora called streamer aurora, which is, I especially like the north-south aligned. So it's like a ray of light coming from the northern to southern field of view. So it pierces through this area, basically. You can see one here occasionally, and then here very briefly. So this can travel between two different bright spots and connect them. So that's why I really like them.
All right. Oh, another question?
Another question online. Victoria R asks, are there special names for the colors in the aurora?
Special
Names for the colors in the aurora.
Oh, that's a good question. I'm not aware of any. Yeah, we just classify them based on shape and duration.
Ray, there's one over there.
I just had one other quick comment. The iPhone is an amazing tool if you want to appreciate the aurora, because when you point your iPhone up at the sky, what you might think are clouds are the aurora. And that green color is from a photograph. It's not as your eye might see it. So the night it was pink and just incredible shooting down, that I could see the colors pretty well. But with the phone, you wouldn't believe what you can see. So I encourage you that, and Aurora Forecast is the website I use that has the NASA with that view of whether it looks like it's going to be bright. But one of the nights I saw it last week, it wasn't predicted by any of them to be really good. It just happened to be good.
Thank you. Another local question. Are you able to tap into any kind of the indigenous knowledge about auroras? Because growing up here, I've never really heard the Athabascans, the Inuit, or the Yupik talk that much about the aurora. And are you able to tap into that? Do you have any feeling on that?
So our public outreach and education office recently put a documentary out called Kiguyat, which it's on GI Alaska, Outreach GI Alaska website, and you can watch the video there where they share some of their stories about aurora. So I am not very familiar with it, but at Geophysical Institute they do have this type of efforts to capture those stories and capture that indigenous knowledge of aurora.
Okay, with that, I think we will wind down. Let's have a hand for our presenter. Okay, thank you. And great questions from the crowd tonight, thank you. And from both here and online. Just a quick announcement about next week. We are going to be hearing from Evans Onyango, Plate to Plate, Rupture of the Great Alaska Earthquake. So with that, thanks for attending. Drive safe on your way home, and look upward. I don't know if it's cloudy out there, so all right.